topic is about respecting the unstable. So to begin with, we're going to talk about the fundamental control problem to give you an understanding of what's going on with all that we're trying to do. We haven't actually talked about control design yet, but it's helpful in analyzing a system to understand that we need to, if we're going to analyze the stability of a system, we need to understand some of the issues that go into the stability of a system. So we've talked about, for example, asymptotic stability and so forth. We've talked about Lyapunov stability. Now we're going to talk about something called internal stability. But before that, we're going to first talk about this fundamental control problem. The fundamental control problem involves finding a practical way of affecting a given system so that it adequately accomplishes the required maneuvers. This must be done in spite of an inaccurate model of the system and in the presence of interfering disturbances. So we have two aspects to this. We have a performance aspect and we have a robustness aspect. So performance aspect is associated with accomplishing what needs to happen, accomplishing required maneuvers. So there are requirements involved here. The maneuvers are what are the things you're asking the system to do. Adequate means there's some measuring or some sense of what's valuable in all of this. Robustness is associated with the fact we don't exactly know the system and there may be actual external disturbances that are impinging on the system. So an important question in all of this is, where is stability in all of this? So notice that we haven't said anything about stabilizing or stability of the system. The given system might not be stable, for example. However, in order for something to adequately accomplish some maneuvers, obviously the system has to be stable or the system will blow up. Okay? So the issue of robustness also is, if we design a system for a particular model, but our actual system doesn't have that model, then that can affect the stability of the system. Also, if we have interfering disturbances and we have nonlinearities in the system in particular, that can create instability in the system. So stability actually enters completely throughout the entire fundamental control problem. It's an essential part of the fundamental control problem. Now, in our fundamental control problem, this is a common kind of control loop. Okay, this is closed loop control, and we have a number of inputs that may enter our system. R is the reference input, so that's the signal we're wanting to follow. D is a disturbance input that affects our system, the dynamics of our system. N is noise that enters our system here through the sensor process. So notice, for example, the disturbance could arise, for example, suppose our system that we're trying to work with is a cruise control in an automobile. That is, we're trying to set the speed at some constant value, and we want the controller to continually be adjusting the throttle on the engine to keep the system, to keep the car going at a constant speed. So a disturbance can enter, for example, if you are going uphill, for example, or downhill. That affects the dynamics of the system, but it's not something that you're controlling. Okay. So that's the kind of thing that happens in many systems. You may have disturbances. You may have a noise present. For example, certain sensors are noisy, are known to be noisy, like accelerometers and things like that. So, or torque sensors, force sensors, all of those kinds of things are inherently noisy. Disturbance. The disturbance, in general, we assume it has low frequency content. That is, for example, the terrain in an automobile generally does not change very quickly. Okay, so we can think of that as being a low frequency signal. The reference signal we generally think of as being relatively slow in frequency. So, for example, a constant input is that's DC. That's about as low frequency as you can get. The sensor noise, however, in general, will have high frequency content associated in that noise. So, in terms of the control problem, we have a plant and we have a controller that we're trying to work with. And so, given these, notice we have three inputs, R, N, and D. We have two outputs, Y and U, at least the way it's represented here. And so we can actually go through and and write the equations. Y of s is equal to n of s plus p of s times d of s plus u of s. And d of s this should say u of s is equal to k of s r of s minus y of s. So all of this becomes this equation. Okay, so that is, I can take the y and the u over to the left side of the equation, factor it out, and I get this, and everything else remains behind, and I get this. So I want to solve for y and u, and I get these. I can go through and show that this matrix can factor into these product of these three matrices. We've seen this factorization before. In this case, we're not working with symmetric matrices, but this factorization still works. You can go through and multiply this out and show that that holds. And one of the nice things about this is because I have an identity here, that I actually have the identity inverse appearing in here, but it's simple because it's just the identity. So I can factor this matrix this way, and one of the reasons for factoring it is that we can actually now take the inverse. So notice these are all block matrices. This is not a 2 by 2 matrix. This is a 2 by 2 block matrix. And so we can't just use the nice simple 2 by 2 determinant, inverse form. So, but I can take this product now, and I can take the inverse of this matrix by taking the inverse of this product in reverse order. So this inverse of this matrix is this. The inverse of this matrix is this. Notice how simple the inverse of this is. It's just multiplying by a minus sign by the k here. So I can show that if I multiply these two matrices together, I get the identity matrix. And this matrix in the middle, I invert this guy, which is simple, and then this is just this quantity inverse. So all of this, the inverse is simple for this, whereas it's not simple for this. Okay, so I can compute the inverse, and now when I solve for y and u, I get this expression. So here's that matrix inverse. When I multiply this all out, actually when I multiply these two guys out, I get this matrix. That is, I get 6 transfer functions associated with each I get a transfer function between each input and each output. And so, for example, this is the transfer function from d to y. This is the transfer function from n to y. This is the transfer function from d to u. This is the transfer function from n to u, and so forth. So we get 6 transfer functions coming out here. Okay. And so if I go ahead and multiply this all out, these are the transfer functions that I get. I can actually write down their expressions for them. And so it turns out that we actually, in order to investigate something called internal stability, we need to be able to look at all the important transfer functions in this system. Because, for example, if our system was originally unstable, then notice that this transfer function has p of s appearing in it. So this transfer function may have unstable poles, whereas this transfer function, for example, may not have those unstable poles because the p isn't in this version, and so forth. So we have different things that come about in this whole process of looking at these different transfer functions. And so we can talk about the internal stability of a system. That is, the system we can show is internally stable if all 6 of these transfer functions are stable. So notice now we're not looking at it in terms of bibostability, we're looking at this in terms of internal stability. Okay? But yet we're still using transfer functions, which implies an input and an output. So it's a little bit different way of looking at stability than the bibostability or the asymptotic stability. So this system is internally stable if all 6 of these transfer functions are stable. So since this is a linear system we're looking at, really what's happening here is this is a way of looking at transfer functions and assessing the whether the well, anyway, that's what we're looking at. We're looking at those transfer functions. So again, this what we call internal stability still is not asymptotic stability. You can go through and show that we might not have asymptotic stability even if we have what's called internal stability. So we've looked at external stability, which is bibostability. Now we're looking at internal stability. So it turns out we can actually simplify the problem down to 4 transfer functions instead of instead of the 6 transfer functions. Notice that that we don't have transfer functions with respect to the R. So this situation actually eliminates one set of transfer functions. We could alternately eliminate n instead of r, but those are the two possibilities. And so the thing is that there's no transfer function between n, where n enters the system, and where r enters the system. So it turns out we could eliminate either one of those two, and we still get we can still evaluate internal stability. Okay. Now, in looking at the overall control problem, there are two transfer functions that are particularly significant. They're called the sensitivity function and the complementary sensitivity function. Okay, so this transfer function is really the transfer function, or we can look at it as the transfer function from R to E, and the complementary sensitivity function is the transfer function from R to Y. So that's basically what we're looking at. So the reason why this is called the complementary sensitivity function is because the two of these added together always add up to an identity matrix. So it doesn't matter what what one of these is, because of the fact that the way this loop is set up, the sum of these two transfer functions is an identity. Okay, so we have that situation. Now I can actually take the 4 transfer functions that I defined and write them in terms of the complementary sensitivity function. So for a single input, single output system, I can actually write it this. I can write it this way. So notice that in this case, these are not, even though I have an I, this is really 1. This is a scalar. These are all scalars. So in this case, TC is written this way. So I can actually write the transfer functions in terms of the complementary sensitivity function. So this is the fundamental control problem, and looking at some basic notion of internal stability. So next we're going to look at the stabilization problem. What happens when we try to stabilize an unstable system? What's happening with all of this internal stability?